Good morning, students. This is the second revision class of concept revision class of topic continuity and differentiability. Here, a question: the function f(x) equal integral part of x plus modulus of 1 minus x where x belongs to -1 to 3 close interval. Then f(x) is not differentiable at. Here we know that greatest integer function is everywhere continuous differentiable except integral point. Modulus function is continuous at its root but not differentiable. Here this is not differentiable at x equal to 1, and this greatest integer function is not differentiable, not continuous at integral point in given interval. Here we use property on algebraic operation on differentiable function. Let f and g are two functions. If both are differentiable, then their addition, subtraction, multiplication, division are necessarily differentiable. If any one of the two non-differentiable, then addition, subtraction, sum of two functions or difference of two functions necessarily non-differentiable. No need to check differentiability. But multiplication and division in these two cases may or may not differentiable. We have to check for that. But if both functions are non-differentiable, then their addition, subtraction, multiplication, division may or may not differentiable. In each case, we have to decide by using any of suitable method. Here, this is not differentiable. This function is not differentiable. This is the f(x) is the sum of two non-differentiable functions. Here, sum of two non-differentiable functions. So f(x) may or may not differentiable. Here, we do the question: x lying between -1 to 3. Here integral part between given this interval -1, 0, 1, 2, 3. First of all, we rewrite the function. When x lying between -1 to 0, in this case integral part -1, x is here, 1 is here, x less than 1 but 1 greater than x. So 1 minus x is positive. Here 1 minus x here. So in place of this we write -1 and in place of 1 minus x. So after cancelling 1 and -1, y equal to -1 in case of -1 to 0. When second situation, x lying between 0 to 1, obviously integral part 0. So this becomes 0. Here again 1 greater than, x is here. So 1 greater than x, 1 minus x positive. After calculation, we have 1 minus x. When x lying between 1 to 2, here integral part is 1, but x 1 less than x. Here x is between 1 and 2. So 1 in the left of x, so 1 less than x. 1 minus x is negative. After removing modulus, this will be x minus 1. So we have x in this case. When x lying between 2 to 3, integral part of x is 2, x is here, obviously x less than, greater than 1 and 1 less than x. So 1 minus x is negative. After modulus, this will be x minus 1. So in this case, we have 1 plus x at x equal to 3. Integral part of 3 is 3 and 1 minus 3 minus 2, modulus of minus 2 is 2. So 5. Now we have to check differentiability. First of all, here change point is 0, 1, 2, 3. At 0, left hand limit 0, right hand limit 1 and value 1, so not discontinuous at 0. At 1, left hand limit 0, right hand limit 1 and value 1. At 2, left hand limit 2, right hand limit 3 and value 3. And at 3, left hand limit 4 and value is 5. Clearly not continuous at 0, 1, 2, 3. So not differentiable at 0, 1, 2, 3. Now we take point x equal to -1, left hand point. Here continuity, for continuity we check here right hand limit and value. Obviously right hand limit and value both equal to 1, so continuous at -1. Function may or may not differentiable at this point x equal to -1, so r f dash -1, limit s tends to 0, -1 plus h minus f of -1 by h. We write here formula of differentiability at a point -1. Limit s tends to 0, minus of -1 plus h minus f of -1, obviously f of -1, this is 1, divided by h, we cancelling this and this, minus s by h minus 1, this is finite, so differentiable at x equal to -1. Thus function is not differentiable at 4 points 0, 1, 2, 3. If we see this question in alternative way, we draw the graph of this function. -1 to 0, change point -1, 0, 1, 2, 3. So first write x equal to -1, x equal to 0, x equal to 1, x equal to 2, x equal to 3. Between these two lines, y equal to -x, these two line y equal to 1 minus x, these two line y equal to x, these two line y equal to 1 plus x, that is this, and at x equal to 3, y equal to 5. Clearly there is a jump at 0, at 1, at 2, at 3, so discontinuous at x equal to 0, 1, 2, 3. Function, if function is discontinuous at 0, 1, 2, 3, so necessarily non-differentiable at that point. That's it. The next question, if the function gx equal k under root x plus 1, x lying between 0 to 3 including in point, mx plus 2, x lying between 3 to 5 including 5, is differentiable, the value of k plus m is, here domain of function is closed interval 0 to 5. Function is differentiable means differentiable in this interval. Here gx differentiable in interval 0 to 5. So continuity at change point is assured here. We first here use the condition of continuity. Here value at 3 or left hand limit at 3 and right hand limit at 3. K into under root 3 plus 1 and right hand limit 3m plus 2. This will give 2k equal to 3m plus 2 and let it be equation 1. Also we differentiate g dash x k 1 upon 2 under root x plus 1 lying between 0 to 3 and here m. Notice here we remove the equality sign on end point here 0, 3, 5. Left hand limit at 3. left hand derivative at 3, actually left hand limit of g dash x at 3. Similarly, right hand derivative at 3 means a right hand limit at 3. Right hand limit of g dash x at 3. Here function is differentiable in closed interval 0 to 5. So differentiable at 3 also. So L f dash 3 left hand derivative at 3 equal to right hand derivative at 3. Here L f dash 3 k upon 2 into under root 3 plus 1, and right hand derivative at 3, this is m. This will give k equal to 4. From these two equations, 2k equal to 8m. Here from first equation value of 2k, 3m plus 2, this will give m equal to 2 by 5. So k equal to 8 by 5. Therefore k plus m equal to 10 by 5 equal to 2. So our answer is 2 here. Third one is the function fx 5x minus 4 0 to 1, 4x square minus 3x 1 to 2, 3x plus 4 x greater than equal to 2. Which of the following is not true? Here first option, continuous at 1 2, continuous at 1 but not differentiable at 2, continuous at 2 but not differentiable at 1, and none of these. Here all these three are polynomial functions, so everywhere continuous differentiable. Here the only doubtful point is change point 1 and 2. So we concentrate here this 2.1 and 2 only at x equal to 1. At x equal to 1, here left hand limit and value both 5 into 1 minus 4, that is 1. At x equal to 1, right hand limit 4 into 1 square minus 3 into 1, that is 1. So at x equal to 1, left hand limit value and right hand limit, all these three 1, so continuous at x equal to 1. At x equal to 2, here left hand limit 4 into 2 square minus 3 into 2, 16 minus 6, that is 10. Here right hand limit at 2, 3 into 2 plus 4, 6 plus 4, that is 10, and value again 3 into 2 plus 4, that is 10. So left hand limit 10, right hand limit 10, and value again 10, so continuous at x equal to 2. Here in option B have to also decide the differentiability at 1 or 2. So we first differentiate this function, since the minimum criteria to use this method here, function must be continuous at change point. Here function is continuous at 1 and 2, so we go through this method differentiating both these sides, f dash x here 5. Here we eliminate remove equality sign on change point, end point, 8x minus 3 and here 3, interval 0 to 1, 1 to 2 and 2. L f dash 1, left hand derivative at 1, actually left hand limit of f dash x at x equal to 1, that is 5. A right hand derivative at 1, that is right hand limit of f dash x at 1, that is 8 1 into 1 minus 3, which is also 5. Both are equal and finite, so differentiable at x equal to 1. Again at 2, left hand derivative at 2, 8 into 2 minus 3, 16 minus 3, that is 13, and right hand derivative at 2, clearly here 3. Here right hand derivative and left hand derivative both are finite but different, so not differentiable at x equal to 2. Here we required here not which of the following is not true. Clearly continuous at 1 and 2, this is true. Continuous at 1 but not differentiable at 2, this is again true. Continuous at 2 but not differentiable at x equal to 1, this is the false. This is false, so our right answer is option C. The fourth question is the function gx equal x plus b, x less than 0 and cos x, x greater than equal to 0 can be made differentiable at x equal to 0. Can be made differentiable at x equal to 0 if b equal to 0, b is non-zero, b belongs to any real number and no value of b. Can be made differentiable at x equal to 0. Function will be differentiable. This implies necessarily continuous. So, to make differentiable at x equal to 0, it must be at least continuous at x equal to 0. Function to be differentiable at x equal to 0, necessarily it must be continuous at x equal to 0. So we first use the condition of continuity at 0. Here left hand limit at 0, 0 plus b, that is b, and right hand limit at 0, that is cos 0, 1, and value at 0, again 1. Here left hand limit equal to right hand limit, here b equal to 1. Now differentiating both these sides, here g dash x 1 when x less than 0 and minus sin x when x greater than 0. First we left hand derivative at 0, obviously this is 1, and right hand derivative at 0, r g dash 0, that is minus sin 0, 0. Here L f dash 0 not equal to r g dash 0. So function is not differentiable at x equal to 0. So cannot be made differentiable for any value of b. Our answer is no value of b. Function is continuous. We know function is continuous. Then function may or may not differentiable at the point. For example, all the modulus function fx equal to mod x, fx equal to mod of x minus k, for all real values of k are continuous at k but not differentiable. Here function cannot be made, it is not possible to make function differentiable for any real value of k. Here answer is option D, no value of b. The fourth question is if x cube x square less than 1 and x square greater than equal to 1, then f is differentiable on all real number except 1, r minus set containing two elements minus 1 1, or real number except 1 and minus 1, or real number except minus 1 0 1, or real number except minus 1. First of all, we open this inequality, x square less than 1, so x lying between minus 1 to 1, x square less than 1, x lying between minus 1 to 1, minus 1 1, that is this interval, and x square greater than equal to 1 means this and this interval outside, x less than equal to minus 1 or x greater than equal to 1. So here if x equal to x cube x minus 1 to 1 and x when x less than equal to minus 1 or x greater than equal to 1. Minus infinity to minus 1, here x, minus 1 to 1 x cube, minus 1 to 1 x cube, again 1 to infinity x. We have to go for differentiability at points. Here shorter method is, first of all, we confirm continuity at change point at x equal to minus 1. At x equal to minus 1, left hand limit minus 1, the right hand limit minus 1 whole cube minus 1, and value again minus 1. So continuous at x equal to minus 1. Second change point is 1. So left hand limit at 1, 1 cube, 1. Right hand limit at 1, 1. And value at 1, 1 again. So continuous at x equal to 1 also. Function is continuous at both change point minus 1 and 1. We differentiate this function f dash x, that is 1, x less than 1, minus 1, 3x square, x minus 1 to 1, and again 1 when x greater than 1. Lf dash minus 1, left hand derivative at minus 1, that is 1, right hand derivative at minus 1, 3 into minus 1 whole square, again 3. Both are different, not differentiable at minus 1. At 1, left hand derivative 3 into 1 square, 3, and right hand derivative at 1, this is 1. Both are different, so not differentiable at x equal to 1. Here function is differentiable everywhere except 2 points minus 1 and 1. Here function is polynomial x cube, here polynomial x. Polynomial function everywhere continuous and differentiable. Only change point is the suspicious point, doubtful point, where function may or may not be differentiable. So we here check at only 2 points minus 1 and 1. The next question, the set of points where function f(x) x square mod x is thrice differentiable. Thrice differentiable. Here first option is r excluding 0 plus minus 1, r excluding 0, none of these. Function is thrice differentiable, set of points where function is thrice differentiable. First we redefine the function x square mod x, x less than 0, minus x cube, x greater than equal to 0, this is x cube. Here x less than 0 minus x cube, we split this section in two parts, x equal to 0, fx equal to 0, and x greater than 0, x cube. Clearly function is defined for less than 0, equal to 0, greater than 0. So domain of function is entire real number. First of all, we check continuity at x equal to 0. Clearly left hand limit at 0, minus 0 q 0, right hand limit at 0, 0 q 0, and value x equal to 0, 0. So continuous at x equal to 0. We differentiate here f dash x. Minus 3x square x less than 0, x equal to 0, 0, and 3x square x greater than 0. We have to check existence of thrice differentiability of function 3 times in succession. Again we check continuity of f dash x at 0. At 0, left hand limit minus 3 into 0 square 0, right hand limit 3 into 0 square 0, and functional value at 0 again 0. So continuous at x equal to 0. We differentiate it again, minus 6x here 0 and 6x, x less than 0, x equal to 0, and x greater than 0, here 6x. Again we check continuity of second derivative of fx at x equal to 0. When x less than 0, that is left hand limit is minus 6 into 0, 0, and right hand limit 6 into 0, 0, and value again 0. So continuous at 0 again. This function differentiating this f second double dash x again, minus 6 when x less than 0, 0 when x equal to 0, and 6 when x greater than 0. Here left hand derivative at 0, this is minus 6, left hand derivative at 0 minus 6, and right hand derivative at 0, this is plus 6. Here minus 6 plus 6 both are finite and different, so third derivative is not possible here. Function is thrice differentiable at points in R except 0. So R minus 0. Where our answer is third option C, except 0. Function is thrice differentiable at each point in real number system.